Hello everyone, welcome to lecture 60 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be looking into metamaterial fabrication and metamaterial fabrication technique, especially pattern transfer. Okay, so here's the lecture outline. We'll discuss about the pattern transfer methods, wet chemical etching, we'll discuss about the limitations of wet etching, and then we'll look into dry etching, different types of dry etching like plasma etching, ion beam etching and reactive ion etching, or it is also called ion enhanced etching. So, what is pattern transfer? After lithography, some processes are basically applied to transfer the mask pattern from photoresist into underlying substrate or film known as pattern transfer. So, pattern transfer basically requires lithography and etching. So, here etching process is basically referring to the removal of is called controlled removal of the materials from the substrate or film via some chemically reactive or physical process. So, some exceptions like in FIB lithography where the patterns are basically directly etched without a resist, and in the in lift up process where a pattern resist is used to dissolve an underlying film rather than etching it. So, etching process typically can be categorized into chemical or wet chemical etching and dry etching. So, here is a brief schematic of the etching process. First you deposit thin film of desired material, then you coat and pattern the photoresist, you etch your film using photoresist as the mask, and then you finally remove the photoresist as well and you get the pattern. Lift up process is like this, that you coat and pattern photoresist first, and then you deposit the thin film of desired material. So, films get deposited here also. Then you swell the photoresist with a solvent and then remove the photoresist and thin film above it. So, let us look into wet chemical etching. So, wet etching is a material removal process that uses liquid chemicals or etchants to remove materials from a wafer or substrate. So, in this process specific patterns on the wafer are designed by the masks. These masks are deposited and patterned on the wafer in earlier fabrication steps using lithography. Now, uncovered areas which are not protected by the masks are etched away by liquid chemicals. A wet etching process basically involves multiple chemical reaction that consume original reactants and producing new ones. This etching is widely used in the semiconductor industry to create intricate patterns and structures on wafer surfaces. In microelectronics packaging, it is basically used to shape and modify the dielectric material, something like the polymers and the ceramics. So, wet etching can be described in three basic steps. First, you have the diffusion of liquid etchant to surface of the material that is to be removed. Okay. So, in this process the wafers are basically immersed in a tank of etchant which is basically a mixture of chemicals. Then the reaction takes place between this liquid etchant and the material that is being etched away. So, there is basically a chemical reaction between the wafer surface and the etchant that will do the material removal. So, a reduction oxidation or redox reaction basically takes place. So, this reaction entails the oxidation of the material, then dissolving oxidized material. Diffusion of the byproducts in the reaction from the reacted surface, that is the last one. So, last step. So, in this way the process works. The time for etching basically depends on the amount and the type of the material that you are going to remove. Now, wet etching process is basically of two types, anisotropic and isotropic wet etching. So, in the anisotropic wet etching, as you can see in the figure as well, liquid etchants exhibit varying etch rates on different crystalline phases of the material that results in great or high anisotropy. So, anisotropic wet etching agents something like silicon or potassium hydroxide KOH or tetramethyl ammonium hydroxide TMAH can lead to significant anisotropy. Okay? And etching a 100 silicon wafer with this kind of agents create a pyramid shaped etch pits with flat angled walls. So, here you can see the angle between the etched wall and the surface of the wafer is roughly 54.7 degrees. Now, you can also have an isotropic wet etching. So, isotropic wet etching basically employs a mixture of hydrofluoric acid HF, then you have nitric acid and acetic acid, so all three together called HNA. Okay, that is used as a common etchant solvent for silicon. So, this is how isotropic wet etching looks like. Here the etch rate is basically isotropic, okay, and here the etch rate in isotropic wet etching is basically determined by the concentration of the each etchant in the mixture. Silicon dioxide or silicon nitride often serves as the masking layer that can protect the areas from etching by this HNA, and during isotropic wet etching material is basically removed from both laterally and downwards in the at the similar rate, leading to a broader etch profile, and this lateral and downward etching occurs in both wet and dry etching process. So, wet etching, what are the limitations? So, wet etching is basically used for large pattern sizes, typically larger than 2 micron, and as you see it is an isotropic process. So, you get sloped side walls rather than straight walls. So, wet etching can be combined to subsequent rinse and dry steps, and this increases the chance of defects and contamination. Here hazardous chemicals and conditions are used, so safety can be an issue. Safe disposal of the chemicals becomes very essential. And then undercutting or overcutting and resist peel off can happen if time is not controlled or etch condition changes during the process. Okay. You may also get incomplete etch. This is usually due to the concentration of the temperature not being sufficient. So, the structure profile is basically left behind is usually a rough surface due to local variations in material removal. So, next we will look into dry etching, another method of the pattern transfer. So, dry etching, as the name suggests, is basically removal of material in the absence of any solvent. So, the process was introduced because wet etching has some limitation in its applicability. As compared to the anisotropic nature of the structure in wet etching, dry etching procedures, dry etching produces more vertical sidewalls, but the removal rate is slower. So, this is a typical surface after wet etching, and when you do it with dry etching, you will see you will get straight walls and very nicely done things. So, dry etching is basically a process that overcomes some of the issues of the wet etching, as you see here also. Here the etchant gases are the primary medium for the removal of the material. So, there are basically three main types of dry etching. One is the plasma etching, then you have ion beam etching or milling, and then you have reactive ion etching. So, let us see how plasma etching works. So, here the plasma is a supplier of the gaseous neutral atom that will react on the surface of the substrate. So, upon contacting with the surface that is going to be removed, neutral atoms will diffuse into the substrate, and this will create a volatile product which is then basically removed. So, this is the process, and finally, you will get an etched surface, and the etch rates in plasma etching is typically 1 to 10 micron per hour, which is much smaller than the wet etching. However, this method is more suitable for thin layers, but it will also provide greater thickness control. So, this is how it works. So, you have got this material to be removed. So, you have the plasma gas flowing this way, then you have generation of the etchant species, then it diffuses to the surface which get absorbed, there is a reaction. After that you have desorption and the fusion of this gas into the bulk, which is basically removed by this material, by this gas, flowing gas. Okay. So, here is a more details, like in plasma etching, the chemical etchant is introduced in gas phase, right. So, the chamber is first evacuated before introducing the gas. Then radio frequency electrodes are used to generate the plasma that could ionize the gas, okay. And this ionized gas basically attacks the oxide layer, and therefore, it can remove the layer. So, there are different configurations in plasma etching. So, one is planar configuration, which is basically shown here. Another type of plasma etching is called downstream reactor, which is basically shown here. So, here you see the plasma is basically ignited at high frequency of 2.4 gigahertz, okay, through impact ionization, and the location of the impact ionization is basically separated from the wafer. So, here you do the plasma generation, and then here it goes, okay. So, here is a wafer which is getting etched, and then finally it comes out from here, okay. So, these configurations are basically defined by how plasma is generated and how the substrate is getting exposed to the plasma. So, with two common methods here includes capacitively coupled plasma. So, here the plasma is held between the parallel electrodes driven by RF power, and here the mechanism is that the oscillating RF current basically creates voltage drops around these electrodes, okay, and sustaining the plasma, and it accelerates the ion towards the substrates. Other method is called inductively coupled plasma. Here you have an RF coil to create a denser and more energetic plasma that can be used for etching. So, the mechanism here involves is that you have induced field that is creating energetic electrons that collide with gas atoms, leading to a much denser and more energetic plasma compared to this capacitively coupled plasma. Then you have ion beam etching, which is called IBE also. So, a physical dry etch process typically. So, in this IBE, argon ions are radiated onto the wafer surface as an ion beam, which has got an energy of around 1 to 3 kilo electron volt. Because of this high energy of the ions, they can strike out the materials from the surface. So, you can see it like this, you have this wafer on the jack, you have some reactive gases, this is how the ion beam is falling from the top. Okay. So, here the wafer is held perpendicular or maybe tilted to the ion beam chamber. So, the etch process is absolutely anisotropic, right. Yeah. So, to prevent particle redeposition, a reactive gas is basically added to the chamber, and this gas basically reacts with the argon ions and causes a physical chemical etch process. And this process is assisted by surface chemistry that forms volatile etch products, and that provides cleaner and faster etching. So, partially the gas basically reacts with the surface and is also with the striked out particles to form gaseous byproducts, and the striked out material and the gaseous byproducts are basically exhausted by the vacuum pumps that you see here, right. Now, what are the drawbacks of this ion beam etching? The selectivity here is low because there is no differentiation between individual layers. Almost every material can be etched using this method. However, there is another problem is that the particles can redeposit on the wafer or the chamber walls, since the reaction product are not in the gaseous phase. And due to the perpendicular radiation, the aberration on the vertical wall is very low. So, you get high anisotropism, and because of low sensitivity and low etch rate, so this process is not a very popular one in today's fabrication process, right. Next, we will discuss reactive ion etching. Now, reactive ion etching combines plasma and ion beam etching process that allows you to achieve both selectivity and directionality. So, there is a the notable difference between reactive ion etching and the isotropic plasma etching is basically the etch direction. So, in the reactive ion etching, it is a much stronger etch and it basically provides a directional etching. In this case, the plasma will basically etch in the downward direction with almost no sideways etching. Okay. So, in the reactive ion etching, a isotropic etch profile as well as anisotropic etch profile is possible. Therefore, the reactive ion etching process, which is a physical chemical etch process, is the most important process in the metamaterial manufacturing for structuring various films. Now, reactive ion etching inside the RIE, that is a process chamber, the wafer is basically placed on a RF or high frequency electrode. As you can see here, this is the high frequency electrode, this is the vacuum of the exhaust. Okay, there is a chiller as well. Okay. Now, this is like a point for gas supply and this is where your plasma is. Okay. By impact ionization, plasma is getting generated in which free electrons as well as positive charges, charged ions are also present. Now, if high frequency electrode is at positive voltage, free electrons accumulate on it and cannot leave the electrode again because of their electron affinity. Now, if the electrode charges up to minus 1000 volt, that is the bias voltage, the slow ions which could not follow the first alternating field are now moving towards the negatively charged electrode, right. So, in this case, if the mean free path of the ions is high, the particles impact on this wafer is almost perpendicular, right. So, in this case, the material is basically struck out of the surface by an accelerated ion. So, it is basically a physical etching. In addition, some of the particles are basically reacting chemically with the surface. So, in this process, lateral sidewalls are not affected, so that there is no aberration and the etch profile remains anisotropic. And here the selectivity of reactive ion etching is good. In addition, the wafer surface is damaged by the accelerated ions and that is why they need to be cured by thermal annealing. The chemical part of the etch process is basically done by reaction of free radicals with the surface and also with the physical milled out material, and this is done in such a way that they cannot redeposit onto the wafer or the chamber walls as it was in the ion beam etching. And by increasing the pressure in the etching chamber, you can reduce the mean free path of the electrons. Okay. Therefore, what will happen? There will be more collisions and the particles heading into various direction will be like colliding with each other, and this will cause a less directed etch. Okay. So, you can get more isotropic etch profile if you increase the pressure. Now, we will look into the process steps in this reactive ion etching reactor. So, in a RI chamber, there it basically consists of two electrodes. Here you can see the number 1 and 4, and they create an electric field like this, which is marked as 3, that is meant to accelerate the ions, these ones, towards the surface of the sample. Okay. So, that is the sample surface. So, the area labeled as 2 basically represents the plasma that contains both positively and negatively charged ions in equal quantities. Now, the ions are basically generated from the gas that was basically pumped into the chamber. And what are these gases? They can be typically oxygen or CF4. So, here in this particular diagram, you can see CF4 has been pumped into the chamber and you are getting a plasma made of many fluorine ions, right. Now, the plasma is initiated in the system by applying a strong RF field to the wafer platter. Now, the field is typically set to a frequency of a few megahertz applied at a few hundred watts. Okay. Now, ions formed in the plasma are basically accelerated towards the surface and mask openings in the RIE The reactive neutral species, something like the radicals, are also generated in the plasma and reaching the surface without any preferential reaction. So, when both ions and the neutral species are present, especially on horizontally oriented surface, something like the bottom of an etched pit, a highly sensitive reaction could occur that will result in the removal of the target material. Okay. So, here you can see the chemical etch is basically enhanced by this ion bombardment, right. So, what it shows here, this is basically the substrate, this is a photo mask. They have these ions which are bombarding, there are some neutrals, and this is the electric field that is working. So, what we understood, to conclude, we can say that RIE basically combines the benefit of both chemical etching as well as the physical etching processes, and it offers high selectivity and anisotropy, which is a very good thing. It exhibits high sensitivity, making it etches only materials with desired composition similar to that of chemical etching. Now, RIE is highly anisotropic, as we mentioned. So, it can primarily etch in a single direction from the mask opening, akin to a physical etching. And the process in RIE relies on energetic particles generated in the plasma that basically activates the chemical reaction on the surface. So, it is employed to transfer fine patterns from a mask or a photo mask onto a wafer. So, that is why it can be used to create deep high aspect ratio tranches and vias in substrate material. So, with that we conclude this lecture. We will have a short discussion on the characterization methods of metamaterials in the next lecture, and that will also conclude the course. So, if you have any query regarding this lecture, you can drop an email to this email address dept.sikdar@iitg.ac.in, but make sure you mention the course title and the lecture number on the subject line. Thank you.